So thank you, Mike, for the very kind introduction. Yeah, it's my great pleasure to be again in Berlin at Bob, and was a little bit surprised to be invited to give a keynote. But I really love this topic, and I hope to share this excitement about it with you. So my talk will be about local first software. And before I go into the nitty-gritty details, I would like to have a head count. So who of you in the audience is developing an application that allows users to share data? Any user-facing app where people put some data in and others can see it? Okay, quite a few. So which of these applications works if your server goes down? So can the users do something? Okay, 2 more. And what happens if you lose internet connection? Does your app still work? Okay, a few people are nodding, 2 or 3. So starting with a famous quote by Leslie Lamport, one of the pioneers, of course, in distributed systems. He has this interesting definition of what a distributed system is, namely one where the failure of a computer you didn't even know existed can render your own computer unusable. Back in the days when he gave that quote, of course, nobody was wondering about mobile phones and so on. It was maybe more about servers. But the situation has not really changed, and I think this is a very on-point description of what distributed systems are, and also why they're so difficult and nasty to handle somehow. Let me start with a little tale. With a little tale, just to show you where this problem comes from and how normal users, so not necessarily software developers like most of you will be, experience the pain of working in a distributed world. So let's assume we have 2 people here, Clara and Marie. They want to organize a workshop. And of course, they need to have some form of document where they write down what they want to do. And one of them, slow. Let's do it like that. So one of them wanted to start, so she took Word, started to write down the workshop proposal, and what happened 10 years ago, maybe 15 years ago, I heard that it still happens with some people nowadays. What they do is, they write an email, put the document into the appendix, send it over, and hope for the best. So what then happens is the next person picks up the document, starts modifying it, adds their ideas, and of course sends the document back. Right? And it goes back and forth and back and forth. What you maybe see here is that interesting things happen to the name of the document, because you need to know which version you're working on. And eventually what will happen is this, that they start working concurrently without telling each other and kind of falling out of this, I'm sending the email, you're sending it back pattern. Yeah? So eventually you will have different versions. Different conflicting versions because of changes that were not done in a sequential fashion. And at some point, you look at your mailbox or look at your folder, and the question is, which one of these versions is the one that you actually want? Is it any of those? Maybe you want to merge some of those. Which changes happened when and where? This is, of course, a situation that is undesirable. And what happened in the last decade, I think COVID also gave it a great push, is that we started to stop sending things around, but rely more on cloud services to manage our documents. And there is a huge variety of those that you can choose from. Some are open source, some are proprietary, some will be hosted by service providers that charge you for your data, well, for nothing, but want to see what you have in your data. Some will be hosted by your own organization. Sometimes you have the choice of what you use, sometimes you don't. So what they would do nowadays probably is put their file into one of these services, and then everybody can edit at the same time. Anytime, anywhere, even offline. But what happens then somehow is exactly what we saw before. You still end up with different copies. You still don't know what happened in these different copies, how to merge them, and what the intention actually with these copies were. And you still have angry coworkers that don't know what to do. There's, of course, one option how to enforce that no conflicts are happening, namely enforcing mutual exclusion. Yeah? So if Marie, for example, if Clara wants to make sure that Marie does not change her copy, she can, of course, lock the file. Yeah? And locking files is great until somebody else discovers that they were locked. Yeah? And then this whole promise of we use the cloud and everybody can work on the same document at the same time simply just falls down. So the reason why our world is so complicated and why these problems occur in practice is not just because cloud providers, service providers don't know how to build these types of systems. There's an inherent issue that was early on formulated and formalized and formulated in the so-called CAP theorem by Eric Brewer, and then later even proven correct. The CAP theorem, the name comes from the three words consistency, availability, and partition tolerance. That's where the CAP kind of comes from. And what we mean with it is that with consistency, what you want to achieve that every read of every observation of the data has the most recent updates, the most recent writes in them, or you get an error that you can't see it at the moment. Yeah? So this way you would make sure that consistently everybody sees the most recent version of the data. In particular, all nodes, all entities, all users have the same data at the same time. Yeah? So it can't happen that you peek at your neighbor's mobile phone or computer and would see different data. Availability is the property that every request, either read or write, receives a response. Yeah? So if you want to open a file, it should open. If you want to submit some change, it should be able to submit it, and you should receive a response that it worked. And availability in this context also should ensure that you receive a response even if some of the nodes are down. So if some of the participants are down. Finally, partition tolerance is the guarantee or property that the system continues to operate even when network failures occur between the nodes. Yeah, so even if the internet is down, the system should work and should be usable by clients. Now, what the CAP theorem says is that if you have a distributed system, in particular a distributed data store, you are only able to provide 2 out of these 3 properties at the same time. So you cannot have a system that is consistent, available, and partition tolerant. And this means that you need to make a choice between these 3 properties. Now, the thing is, partition tolerance, controlling whether the network is down or not, is something that we typically can't do. I have no control over network switches that are placed in an arbitrary place somewhere in the world. Yeah? So partition tolerance is just something we need to live with because this is our physical reality. And if we want to make sure that the system works even if the internet is down, then we need to put an emphasis on either consistency or availability in the design of our systems. So-called CP systems tend to forget about availability, but focus on consistency, making sure that whenever users see the data, they either see the most recent version, or they get an error, which is okay with partition tolerance, right? In order to implement such a system, you need to have some form of enforcement to make sure that there is always a most recent version, that there is no concurrency. So somehow either ensure mutual exclusion, that only one client can edit the data at any time, and these edits mark the most recent version, or you need to run some protocols like a consensus protocol like Raft or Paxos that orders all the updates in an order, and then you kind of know where to, how the system evolves and have kind of a linear evolvement, and this is good. However, reads and writes might be blocked. Yeah, so you either see something and this is consistent, or you're blocked as a user. Other systems put the focus more on availability, so they are not so much worried about that users see exactly the same things at any point in time. If you put your focus on availability, this means that users can concurrently at the same time edit the same data. And this, of course, means that there might be conflicting changes, and that you somehow need to resolve these conflicts. It's not really a good conflict resolution strategy to give the users two versions and kind of say, well, choose whatever you want, right? In some cases, it's maybe the right choice. At least no data gets lost this way. But this conflict resolution is something that you, in this context, actually really need to worry about. And the other thing to keep in mind is that reads might observe updates only eventually, meaning users not necessarily see the most recent version, but some valid version, and only, if they go online, if they receive updates and so on, their view will kind of progress and they will see more recent entries. And local first software is exactly one of these AP systems, so focus on availability and partition tolerance. Martin Kleppmann, who's one of the very prominent persons and researchers on local first software, framed it kind of very nicely akin to Leslie Lamport's citation that in local first software, the availability of another computer should never prevent you or your clients from working. Yeah? So you want to actually work seamlessly on whatever device you have, whether or not you are connected to the cloud, whether or not the cloud server works, whether or not your coworkers are online and working. Now, this is something that is a kind of nice and desirable goal. The problem comes from the fact that in our system architectures, we currently rely a lot on servers. And this is, of course, problematic for several reasons. One of the reasons is that latency is a problem. So just by physical reality, updates that are done in the US won't be necessarily instantaneously visible in Asia. Yeah? When somebody makes an update in Australia, typically this will take several hundred of milliseconds, sometimes even seconds, till it's visible in Europe. Yeah? And there is a real physical limit. Information can't travel faster than light. Yeah? So there is actually really a physical limit. It gets very interesting. So I have a colleague who started a workshop on interplanetary communication. Yeah? Maybe someday we will be on Mars, and then this reality becomes even worse, right? So latency is something to worry about. Dependence on network is something to worry about. I always make the joke that we're in Germany, right? So to a German audience, I typically don't need to explain that there are places in the world where you don't have internet connectivity, right? It's funny, international people are always like, yeah, but I have internet kind of everywhere, even in the subway. And I was like, yeah, but I don't have it in my garden, right? And then we, of course, also have a dependence on service providers for non-technical reasons. So if you put your data onto a service, onto a service that is offered, the lifetime of your service will be determined by the lifetime of the service provider. If they go out of business, you have a problem. You're also dependent on their business model. If they decide to charge you more for your data, more for your service space, you probably will pay it because otherwise you are out of business. And also data ownership is a thing. Typically for services where we as users don't pay anything, it's the data you pay with. Yeah? So there are a lot of analytics run, machine models trained on that. Yeah? So you don't own your data. Necessarily you don't know what happens to this data. And this led in the local first community to a little kind of manifesto that is summarizable in 7 different points. First of all, so the goals that we want to achieve are that we can always work without delay. Yeah? So we don't want to see any spinners in our application. We don't want our work to be trapped on a single device. We want to be able to share data with others and with ourselves on different devices. Connectivity of networks should be optional. We want to have seamless collaboration, online collaboration with our colleagues. We want to make sure that our data is accessible for a long time. Security and privacy should be concerns by default. Yeah? So you want to retain ownership of your data and also control of your data and potentially also of your software. this is, I think, a very nice and succinct summary. What I will do next is I want to zoom in into a few of these points just to make sure that, that we have a bit more background on that. So first of all, what is meant with no spinners? In the early days of the internet, so in the first decade maybe, the typical way web pages worked, web applications worked, is that we had somewhere a web server that was serving HTML pages to clients that were rendered in the web browser. Whenever a form was clicked, data was sent to the server, potentially using CGI scripts going to the database, rendering new web pages, sending back the HTML. Yeah, so very classical. Before that, I should mention everything was in essence not just local first, but rather local only. Yeah, I mean, there were some servers and so on, but this is kind of where, yeah, a whole new market and a whole new world kind of started. With the rise of JavaScript, clients became a bit fatter, as they were called. So we had a bit more JavaScript on that side. When we submitted our data, we still had this application server that was sending HTML back. And because this rendering of accumulation of HTML here in the application server turned out to be non-desirable, what happened eventually over the next decade was that these forms and so on were actually replaced by REST. So you would rather send a REST request, kind of keep the HTML page, and then dynamically send part of the data and re-render only parts of that data again. And I believe a lot of applications nowadays still work like that. So zooming in, if you press a button, what will happen is that in your JavaScript part on the client side, an event handler will be triggered that will send a request to the REST API server that handles the request by potentially going to a database, getting data, and calling back. The problem there is that we now have the REST API callback a long time after we click the button. And this is typically the time that users needs to wait. And this time is actually dominated not necessarily by the API server typically, but rather by the latency of the internet. Yeah? So the time it takes to travel to the data center where the server is hosted and back requires the user kind of to wait. Yeah? And just to remind you, latency is a thing. Yeah? So this can take several seconds, and you know it's the time when users continue clicking buttons in order to make sure that it really works, because why is the button not working? What we actually want to have is that instead of going the whole way to the cloud in order to get our data, we want to actually prefer to have our data on some local storage. Simply just go to the local storage and do this loop in a very small fashion. And only in the background, sync whatever we have in the local storage with our cloud part. Maybe have a sync service there that also makes sure that data is persistently stored in some database or file system or so. And whenever there are changes by other clients also on the data, the sync service should actually be able to push these updates into our local storage, where you should have then handlers installed that react on that. And this, of course, can happen then several times. And this is an architecture that is very predominant in local first software. Yeah? So having maybe not the full data of an application stored on your device, but the stuff that users are interested in and the parts that they need in order to be able to work offline or work independently from others. Yeah? And the sync service here is then actually doing the hard work of making sure that we have a consistent version and view of our data. The other aspect I want to zoom in a bit is this aspect of the long now, because I find this very fascinating, and I don't think we have an answer to that yet. We have data stemming back from a long time, several thousand years. We still have that data. It's, for example, on clay tables like this, and if you study long enough, you will be able to decipher it and learn what that means. We are still able to do this nowadays. Other projects, so not this beer allocation resource, but other projects were not so very successful in making sure that data survives for a long time. So I'm not sure who's aware of the Doomsday Project. In the 11th century, like on Christmas 1085, I think, William, King of England, decided that they need to write down in some legally binding form who owns which part of land in England. So they made a census, they kind of counted how many houses, how many mills, how many farms there are, put everything in 2 volumes of book, and this became the official land registry of England, the one that is supposed to stay there till the end of times. That's why it's called Doomsday. And it survived. It survived till today. Eventually, people thought that's actually a cool thing. And for the 900th anniversary of the Doomsday, BBC, in cooperation with several technology companies, among them Philips, decided in 1986 to bring out a multimedia edition. So what they did is they went to schools. I think several hundred thousands of school kids were involved, collecting information about this day's England, making videos, making audio recordings, pictures, writing texts, and collecting all of this in order to make this nicely accessible and also navigatable in a modern way. A new computer or a new device, I'm not sure if this was especially done for that, but it seems feasible, was designed. It was the BBC Master Advanced Interactive Video System, and with the system, as you can see here, there was a specific dedicated keyboard and other interfaces, touch interfaces, and so on, that help people to navigate in this data. Any guesses how long that lasted? Well, not so very long. Probably around 5 to 10 years. So there were a few places where these machines were kept alive, but eventually people kind of gave up, and this data was threatened to be lost. So they were stored on these specific disks with 300 megabyte of device storage. Okay. So in 2011, the first rescue project kind of started. That took the system and turned it into some web resource, so hopefully into a format that was more accessible for other people. And I put it online in 2011, and they took it offline in 2018 because it was a lot of work to kind of keep this updated. So if you want to see this now, there are still a few libraries in England where you can go actually see it on these devices. Also, you can go to the National Archives in London, I think, or somewhere in Britain, and see it. There were a few more rescue missions, also trying to see if this navigation system can be preserved. There are a few emulators built, so people are still worrying about how to keep this alive. Now, the timestamp between this one and this one is, I don't know, 30, 40, 50 years, right? The stuff from the 11th century is much more accessible to us if you read Latin and so on. But we can still read that. We can't read what is on these disks. Yeah? So there's really a danger of us losing data. And there are, of course, several ways how to escape these digital dark ages. One of them seems to be to rely on open standards. So the US Library of Congress formulated that XML, JSON, SQLite are desirable standards that they hope will survive for a very long time. And a lot of data is currently stored in these data formats. Also, of course, making sure that we have the right hardware, that we have redundant and replicated storage. This is things that people nowadays, actually, librarians really worry about and put a lot of effort into. One thing that became clear on the way is that it's probably not enough to just have the data, because if you just have the data but not the software to use it and to run it, you have a problem. Yeah? And you might also be aware that there are a lot of initiatives currently trying to rescue old computer games, old other things. There's also already a lot of data that has been lost. Maybe for some of this data it's not such a pity, but I selected here just a few of many, many, many thousand services and applications that I've seen disappear over the last 10, 15 years. And I know a lot of people put a lot of effort and work into those, and this data is gone. Yeah, so there is, for example, even just a very long Wikipedia list dedicated on services that Google at some point stopped. Yeah, all the data that you have there, even if you are able to export it in XML or JSON or something, unless you know what to do with this data, you probably know, a lot of other people don't, this is stuff that is lost. And this is something we actually as a community and as a society should put emphasis on. So the next point on which I want to continue a bit now is this aspect of seamless collaboration with your colleagues. What we want to do with local first software is that we want to work concurrently with other users on the same data. There are a lot of applications where this is actually essential, necessary, and used nowadays already. In particular, office applications, project management tools, games. So whenever people stick together and want to get something done. And you typically don't want to wait till the email arrives with the new text. Yeah? So you want to have applications that work, that are reactive, and that seamlessly sync data between you and the other people working on them. What we in particular want to have, that it's safe, meaning that it does not get corrupt or anything with these concurrent edits, that our intentions are preserved, and that the data stays secure. Now, this is nothing that you get simply just for free. And I will show you a few examples why this is the case. So let's do a little bit of a dive into techniques for local first software. What's the secret sauce? So how do we actually ensure that these different versions merge into something that is useful and correct? If you have concurrent updates on the same data, you sometimes have interesting effects. Yeah? This is from the early days of the system that is now no longer called Twitter. Yeah, so depending on how many devices you use in order to unfollow people, you can have a negative following count and be very, very unpopular. So how does this actually work? I have a little demo for you that Philip, who is standing over there from our team, assembled for me. I will sit down because I need to type a little bit. Where we want to highlight or want to showcase how divergence in data kind of happens. And so what we have, for example, here in this demo, you can also download it later if you want to. I can give you the link. What we simulate is a network that does interesting things. So sometimes messages get duplicated, sometimes they get lost. I should mention that these techniques for local first software, so-called CRDTs, we'll elaborate on that in a minute, comes actually from the database community. And in the database community, they don't worry so much about single users, but they have different replicas on the client. The techniques are exactly the same because the problems are exactly the same. We have data and we have replicas of this data. And we want to have multi-masters, or multiple entities that can update the data at the same time. Yeah? And if the network does weird things, and networks do weird things, as you can see, it's not given that all the clients converge on the same version. I can show you here what happens if you have a simple counter. So a simple counter being 1, where if you update the counter locally here and send then the updated version, the new version, to the other clients. This kind of works if only one client is doing this, and the network is fairly okay-ish, right? Then you can, see your data travel. Eventually, it reaches the other replicas, and they get the same updates. It gets more interesting if you have interfering updates, because if you simply just replace always with the new version that you get, you diverge. Yeah? That's not very surprising. I sometimes have people that then say, well, I just put a timestamp on it, and then the timestamp will sort out what the most recent version is. This is correct. So if I had added timestamps to these and always filtered for the most recent version, every node would have had the same version, but you have data loss. Yeah? Because if I update on client or on replica 1 here a couple of times and then more recently update here once, then this was This was not useful because I need to reset the simulation. Yeah, so if I update this here a couple of times and then only increment here once, the last thing I did was incrementing here once, you will fall back to value 1. Yeah? And this is not very useful, yeah, because this means that all the updates that happened in between will simply evaporate. This happens with all data storage that promises this last writer wins approach. You have data loss. It gives you convergence, though. Yeah? That's good. What we do instead is add a little bit more metadata to it. Because if we, for example, as seen here, remember how many updates each replica did at any given point in time. Yeah, so we count how many updates replica 3 did, how many updates replica 1 did, and always locally add all these updates together. Then all the clients who have seen the same updates will have the same version. And even better, so if we have clients that maybe did not observe some updates because they were offline, later then observe a new update, they will learn about everything they missed in between. This is the implementation of a so-called state-based counter. Yeah, state-based meaning that all the states, or all the things that one replica knows about a specific data item, is shared with the others. And this has some anti-entropy, so making sure that the knowledge does not diverge too much. This is then kind of baked into that system. Yeah? And this state-based counters are provably some of the systems where in such a replicated view of the world, different versions will converge. Another, just to show you that there is kind of a richness of different data types that can be handled with this. I have here a set implementation. So in the set, I can add different elements, add different replicas. Should maybe add that up here. Different elements at different replicas. And what you see in the view here is all the elements that have been added by different replicas into the set, and I can also delete them. So that's a replicated set of things. Now things get a bit more hairy. So for example, if I add here A, and I add here A, come on, and I remove here A, be fast to do that, right? But users are great in doing that. What you can see, so maybe you can't see it down here so well, here A is still in the set because the last operation that traveled to replica 2 was the addition of A. In the other two replicas, A is no longer in the set because the last operation they saw was the deletion of the element. And the second add was kind of idempotent. The element was already in the set, so it disappeared. And you have, again, the replicas kind of diverge. As we've seen with the counter, what we can do now is add some more. Okay, maybe I should start with this one. So with the, let's take that one. So with the set, when adding more metadata that we have here in these different colors, you can see that we have a view. So up here we have the view, which elements are currently considered to be in the set. It's a different order here, reflecting in how they kind of travel, but it's a set. So for the set, we actually don't worry too much about the order. If the element is in, it's in. And down here you can see we have another field where we saw which elements were added, because what I can do now is both here and here, for example, add element D. So we now have eventually still one element in the view. So the user will see D is in the set. And in the background, in the metadata, we know actually that D was added twice. Now, if I want to remove D, it's probably not sufficient to remove just one of them. So I need to remove everything I saw, everything I observed. So if replica 3 here is deleting the D, it's deleting D in all identities that it saw. And this means that On all the replicas, D will be tagged as removed, and it will no longer appear in the view. However, if I now do, no, maybe I should not, I can use D here, can use D here, can remove D here. So what I did was I was adding D in 2 places concurrently, and I was removing 1 instance. This means that there was, in these concurrent operations, there was 1 operation that was an add, so an insertion of the element into the set, that was not covered, not observed by a remove. And we chose, for example, in this design here, that in these cases, this element that was added but not observed by a remove is considered to be in the set. And it's a very dedicated design decision. So you can also decide to do this completely different. You could also decide to kind of say, if there is a concurrent remove of an element, then the element should please disappear also. Yeah? And using the right metadata and the right conflict resolution schemes, you can implement it like that. What you can here also see is that these elements here, we are able to re-add an element after it was removed. This is not a given. So there are replicated data types out there that don't guarantee this. So this delete double set here does that, for example. Yeah, so so in this design, if I remove A, it's added here to the set of removed elements. And if I now add it again, then it does not disappear. It does not reappear. That's a so-called 2-phase set. For every element, I only have 2 phases. I can add it once, and I can remove it, and then it's burned. I can't do anything with it ever again. This kind of works because it still gives you a consistent view of the world, but you as developers know that you then need to work around and make sure that item identity kind of becomes different and so on. Some people try to come up with a new trick, kind of counting how often an element was added and how often it was removed in order to make sure that things kind of work out. This has a slightly weird semantics, so it still converges, but it has slightly weird semantics because this means that you can delete an element 5 times and add it 3 times. So in order to have it back in the set, you need to add it 2 times again. Yeah, and this, it's possible, but it's quirky. Yeah. So what we want to do is actually come up with data type designs that cover the intention of the server, of the user in what we are doing, that reflect the semantics of the underlying data type, so reflect the semantics of sets, of counters, and similar. And what is also a challenge, as you can see here, if we have elements here, every time we remove something, it does not really go away. Yeah, so we accumulate in the back metadata and additional data, and this is biting us at some point. Yeah? So if you have a lot of changes on the data, it might be that your metadata is growing and growing and growing. By design, these data types here have a monotonically growing state. This is kind of the secret sauce why this works at all. But you actually want to make sure that this is garbage collected away at some point or removed by other things. And there are nice tricks out there that show how this can be done. So this was a quick detour on how CRDTs work in the back. There have been a lot of CRDTs designed for different use cases. Let me just do something. So I have a few fallback slides just in case something did not work out, right? If you want to learn more about CRDT semantics, please feel sure to grab me in the break. Yeah, so what we designed over the last decade in research, but also with people who put this into practice, into nice frameworks, is actually a whole collection of these CRDTs. For you as developers, my hint is don't try to invent it yourself. It's actually very subtle to kind of come up with issues. Yeah, and I will show you a few examples where we kind of get stuck even though we know what we are doing. it's a good idea to build on existing frameworks because there are implementations that have been proven correct. There's a lot of research on how to build these things, with a proof that convergence is kind of happening, and you probably want to use what we are doing as academics in order to make your own work more slightly simpler. So CRDTs and local first software, there's a whole focus on collaborative text editing. Yeah? You probably already use some of these text editors with CRDTs in the background. I did not show you how to do sequences. So sequence CRDTs are a thing when it comes to text because text are a sequence of characters. Yeah, but you need to be careful because you probably don't want to only edit text, but you want to make it bold, want to have it in italics, etc. What happens if users do this in overlapping things at the same time? A lot of clever people came up with clever tricks here. One of them is here in the back, Kevin. So he's the originator and curator of the YJS framework. If you have questions on this, ask him. He will also have a tutorial that I highly recommend. It's one of the frameworks that a lot of people use for building their own local first software. You get a library of different data types. We have maps, texts, arrays, also XML. And out of these, you can build your data, your own application. There's also a large ecosystem that helps you to deal with persistent, with update propagation. YJS is architecture agnostic, so you can either build a peer-to-peer system, you can also build a server-client system, like in a star-like fashion. The design of these data types does not worry about who's communicating with whom, whether it's a user-end device or a cloud server. You kind of can make your own architecture very nicely on that. And YJS is actually, it has become famous in the community because it supports many of these rich text editors with offline mode, version snapshots, undo, redo operations, cursor positions, and other things. Another library in that area is AutoMerge. It's one that is created by a research company, Ink and Switch. Martin Kleppmann was also one of the designers of AutoMerge. Again, we have a library of different data types, maps, lists, texts, scalar types. In AutoMerge, the data model is slightly different. So we have documents that are like JSON objects where you can nest these things here arbitrarily. Again, it's architecture agnostic. We have an implementation. So the main implementation nowadays is in Rust with bindings for JavaScript, script and Swift, and other things. Quite a few applications out there also use this. If you don't like objects and prefer SQL and Postgres, there are also a few services that help you with that. So Electric SQL is a startup that is developing a sync service where you put your Postgres server into the cloud, then have this Electric server in front. So this is just a normal off-the-shelf Postgres thing, and Electric here is kind of giving you the magic, making sure that clients can subscribe via a proxy here on shapes. So you can decide what part of the table or tables clients can see, define a shape, register the shape on the server, and then in the back, Electric will push the updates into the local storage of the client, and the client can then work on that. And there's also a way to kind of sync the writes back into the Postgres, making sure also with different techniques that the Postgres is then not diverging and losing data, but doing the right thing. It's kind of nice because if you make your architecture scalable, if you want to make it scalable, you can put these, caches of these shapes also on CDNs, and then you get really, really nice and good performance. Another one where former project partners of us are involved is a service called Ditto. This one has a very interesting proposal because it not only allows to put servers into the place, but it has as service offering a platform where you can either connect to servers or if the server is not working, people that are in local proximity, like us here in the room, could work together on our devices. Yeah? So I could cut kind of the Wi-Fi and LAN here of the hotel, and you would be able to still work together with very low latency using Bluetooth, low energy, Wi-Fi, or even LAN. They have an automatic device discovery and mesh networking, so you really kind of get off the shelf something that works. I've seen a lot of posts showing that a lot of customers of theirs are air companies. Yeah? So on airplanes, internet connectivity is not so cheap, right? But you still maybe want to order your food on the plane on your mobile device. Yeah? So what they do is you download the app, and as soon as you are in the air, you have your local network kind of working. Just as a last word of caution, we are also developing apps, local first apps. So in our context, we here have, for example, the Teens Labbook, which is an application for schools and laboratories that I can visit. Schools also don't have internet or Wi-Fi or so being able there to work offline is very important. Our application is built on YJS. We have a text editor, and because of our use case, we also needed to have a spreadsheet. And there things started to become interesting because there is, of course, no CRDT for spreadsheets as it is for text editors. And on our journey in making a collaborative text editor, a collaborative spreadsheet, we found out that the world of spreadsheets is actually not so simple. So what we observed in some widely used thing, if you share your data via Notion in tables with your collaborators, this is the initial state. Then you have one person being online, does a lot of edits, adds a new column, adds several new columns, adds new data, and you have another person who edits the same spreadsheet offline and comes back from holidays and syncs back all the changes that Bob did is lost. One of these cases where last writer wins is losing data, my guess, because Alice coming online gives her a more recent timestamp probably on the server, so all the other changes disappear. You hate colleagues that go on holidays, right? So we checked with a few other implementations, just have here Google Docs. So in Google Docs, the spreadsheet has also some nice properties. So if you're online, you can cut, copy, paste, insert columns, rows, whatever. And if you go offline, that's the only thing you can do. Yeah? The problem is that it's not so simple. So what we typically do when we come up then with these situations is an analysis. What are the operations that I want to do on my shared data? So for example, in the spreadsheet, editing a cell is perfectly okay with inserting a column. You won't edit a cell in a column that does not exist. Yeah? So these are completely independent operations that commute. You can execute them in any order. Editing a cell, however, conflicts when you delete a column. Yeah? So if you edit, somebody deletes, and then you need to decide what to do. And sitting down and figuring out, deciding what to do is important here. So these design decisions is something that a CRDT framework will not take away from you. Yeah? So you as developers still have a lot of work to do, actually. So typical problem, for example, is what happens if two users edit the same cell? What should happen? I asked a group of people before, so one idea?
I think that you need to decide. It's a business decision, I think.
It's a decision that really depends on your application. And you could take the largest value, you could take the smallest value, you could append both values, you could throw them away and replace everything by null. You could ask the user. You can take the last value written or an arbitrary one. For me, both these things are the same. You can also decide that one person always overrides the other. Yeah? And you can see there is a lot of work to do still for developers, even if it converges. All of these decisions are safe in the sense that you will have a convergent version. But the way your application behaves really depends on your own choice. So you really need to make sure what things you choose. There are also a few limits. Let me just very quickly highlight them. There are a few data invariants that require strong consistency. If you're building a banking application where people can transfer money and you need to make sure that you don't run into the negative, you need to be careful. There are a few solutions to that. You can mix and match things. There's a lot of research done on these things. Come to me if you want to learn more about invariance, how to detect when you actually need something stronger than these CRDTs, how to find this. There are also a lot of challenges in open problems, how to do access control. If two people do the same thing and you take away the right of one, what should happen to his updates? Christian here from TU Darmstadt is doing very nice work on that. He's your expert on that one. Standardized data formats. Make sure that you have a way to export data even if you go out of business for the sake of your users. If you have an application, how can you make it local first without rewriting it completely? I think that's a very interesting challenge that services like Electric are targeting at, because you can keep your Postgres database. Still, you need to think a bit about the conflicts. And causal dependencies. Typically, we have a linear, or we have operations that we depend on. I can only edit a cell if I inserted the corresponding rows and columns before. Now, what happens if I support something like undo operations? What happens to the content of my cell if I undo the insertion of the column? Not obviously clear. Okay, so this was a whirlwind tour through the really large and expanding world of local first software. I want to close with a few very nice quotes by Martin. Just for you to keep in mind, if it's local only, so if you build an app that only one user can use on one device, it's not local first. Yeah? This would be trivial. If it does not work with Wi-Fi off, your application will not be local first. And if it doesn't work, if the app developer goes out of business and shuts down their server, you're probably also not local first. With this, I wish you happy and successful syncing, and I'm almost open for your question. Just one last thing. We are in Berlin. Berlin is one of the hubs for local first. There will be another conference in May, end of May, the Local First Conf, running its second edition. The first one was a great success. There are a few tickets left. If you want to learn more about the community, you're very welcome to grab one. Thank you.
Thank you so much. We'll take 5 minutes for questions. There's one.
Are your slides going to be available somewhere, or?
I can make them
Yes.
available.
That was the question? Okay. There's one. Andres.
I know naming is hard, but I don't really understand why it's called local first.
There were a few proposals of how to call it best and so on. Local first, because it comes from the pain, I think, being able to work on your device locally. The developers that develop that know how Git works and so on, right? So all of you probably, when I showed the first slide, how to share documents, was kind of like, I put it on Git and everything works. This is a reality for us, but it's not a reality for the users out there. Yeah? And they actually want to have software that works on their mobile devices wherever they are, whenever they are. So designing your application with the mindset that when you sit down and open your device and start working, it should work, no matter whether you have internet or not. I think that's where it comes from. And it sells well as a term.
Yes.
Yeah. Has your approach led to new, more semantic ways of changing data? So we saw with the spreadsheets, you could delete a column or insert one, but maybe you just want to move it. And it would be easier to resolve the conflicts if you have this more semantic description.
This is also an option, yeah. So you could move it to the end. You could decide to. There are a lot of different ones, and you're right. So what we discover when you go into a specific application, the semantics of the application should be the one that should help you make decisions on how to resolve the conflict. Yeah? Sometimes people are like, so we have, for example, for these sets, I think there are 4 different variants and flavors out there that people use. Most frameworks, libraries only offer one. And for me, it was initially the question, can I do my semantics with this one flavor that I get? It turns out that most of the cases it actually works pretty well. So the semantics of the application is what should matter in the end. And this makes it also slightly more difficult than other things to verify and so on, because for verification, worrying about the semantics of a specific application, you need to have a specification of the application in Formula 1. and this makes it, I think, challenging. There's a lot of research on that, and I hope maybe in a decade or so we have tools where you kind of say, this is what I did, is it correct? And the tools give you back, yeah, everything's fine. Right now, this requires expert knowledge.
So thank you, Stockholm. Are there any questions from Copenhagen?
This is Copenhagen. Can you hear us?
Yes, we can hear you, Copenhagen.
Do we have any questions here?
Go ahead, Copenhagen.
So we have no questions here. Thank you, Annette.
Excellent. Thank you so much. That concludes our keynote. Thank you again, Annette.